So this is part 1 of homework 5, where we have water flowing through an aqueduct with width W inclined at an angle relative to the horizontal at a volumetric flow rate of Q. Assuming the shear stress at the wetted wall to be equal to that for an equivalent circular pipe with the same average velocity, derive an expression for the height h of the water flowing along the aqueduct. Write Python code using scipy.optimize.root to solve for h when w equals 0.5, q equals 1, and when the aqueduct is inclined 15 degrees relative to the vertical. So as you can see here, I have a little diagram of the situation here with our rectangular channel and the liquid flowing through it in this direction with the angle of 15 degrees to the horizontal, with the flow rate of 1, the width will be 0.5, and obviously we are looking for the height here. So we're going to start off with Bernoulli's equation here. So since this is an open rectangle channel here, our pressure at 1 and 2 are going to be equal to each other. So this portion of our Bernoulli's will cancel out. And then also, from 1 to 2, there's no change in cross-sectional area, so the velocities will stay the same. So this part of Bernoulli's can go away as well. And then, as you can see here, we have this change in z, or change in altitude from 1 to 2. And actually it is from 2 to 1, so this will end up being negative, our delta z here, delta z. And then we can tell here that our delta z is this change from 1 to 2, which is actually the same as our delta x here, which our delta x here is just our length here. So we can relate those through our theta. So we can say that delta z, this right here, delta z is equal to delta x sine theta. So now we can plug that in here, and we'll have g delta x sine theta, and then it'll equal, we can actually cancel out these negative signs because our delta z will be negative, obviously, when we take the smaller altitude minus the bigger altitude. So we can actually divide it by 2 as well, make this 2. F. And then our delta x's will cancel. And we'll have v squared over d. And this will just be g sine theta. So now what we're going to want to look at is the shear stress, and we're going to be using a circular pipe to figure out our shear stress. So we just think about a circular pipe here with liquid just flowing down, and we want to calculate the shear stress of that. We're going to need to account for the weight of that liquid pushing down times the acceleration due to gravity. So we can kind of write out this equation here. It'll be mg equals rho, the density, times A, times delta x, the length, and then still times g. So obviously that there is our weight of the liquid. Then we can also then just write this as the shear stress tau times the wetted perimeter, which is basically all this perimeter of this pipe that the liquid is touching, and then delta x. So then we can say that these delta x's cancel, and we end up with rho g equals tau wetted perimeter over the area A. So now we can find what this wetted perimeter over area actually is. So it'll be, I'm just going to write it up here. For a wetted perimeter, that would just be the circumference pi times d, and then over the area, pi d squared over 4. And that'll just simplify out to 4 over d. So now we can plug that back in down here. And I'm also going to divide by rho on both sides. And we'll end up with g equals tau 4 over d rho. Now what we can do is plug this in over here for g. So now plugging this in, we will get tau 4 over d rho sine theta equals R2 f v squared over d. These d's will cancel. The 4 and 2 will cancel, but leave a 2 on the bottom here. And then we can also multiply by rho, divide by sine theta on both sides, and we will end up with an equation for tau as rho f v squared over 2 sine theta. So now we just need to relate this back to our situation with the rectangular channel. So we're going to go back to this equation here where we had rho g equals tau wetted perimeter over the area. And this time our wetted perimeter over the area is going to be for a rectangle here, where we'll just have 2h plus w for the wetted perimeter, and then h times w for the area. And now we can plug that in here, and plug this in here, and then we will end up with rho g equals rho f v squared over 2 sine theta, and then our 2h plus w over hw. And now we can cancel out these rho's, and we'll end up with an equation for our acceleration due to gravity right here. And this will actually end up being the equation that we can use in Python to solve for our h with the root solver. So as you can see here, I have erased the box around this. This actually isn't the equation that we're going to be using the root solver on yet. I did forget one more thing. We do know this volumetric flow rate, Q, and we know that Q is equal to the velocity times the area, or in this case, we can say velocity times hw. So if we divide the hw over, we can say that v is equal to q over hw. And now we can plug that in here, And now we'll end up with our equation that we will be using the root solver on, where we will have F and then the volumetric flow rate squared over 2 sine theta and then HW cubed. And then up here we'll still have our 2H plus W. And this will actually be our equation that we will be using the root solver on in Python. So one final thing that we need to worry about is this fanning friction factor, F here. So we're going to need Reynolds number, which again is rho VD over mu. And what is really important in there is that D, we're going to have to relate our ratio from the circular pipe to our rectangular pipe. So how we're going to do that is with that 4 over D ratio we had up here for that wetted parameter, and then relate it back to our rectangular wetted parameter, which we had as 2H plus W over HW. So if we isolate D here, we get D is equal to 4HW over 2H plus W. And now we should have all the equations we need to start the coding portion of this video. Again, it's all these ones in the boxes that we will need. So now we can start actually solving for our height of this rectangular channel. So as you can see here, I've already imported NumPy and imported our root solver from SciPy Optimize. I've also already typed out the Churchill equation, which we've done in a previous video. And then I've inputted our mu, rho, g, and this Churchill equation here, where it takes in the Reynolds number and surface roughness and gives us our fanning friction factor. And then I've also just inputted the known values that our problem has stated for us, our Q volumetric flow rate of 1 meter cubed per second, and then our width of 0.5 meters, and our angle theta of 15 degrees. So now we can define our equation, where we're going to be giving it a vector of unknowns, and our fluid level H is going to be the first value in that vector. And then we also know that our diameter D here is equal to 4 times H times our width W over 2 times H plus W. And then now we can define our Reynolds number. And we also have that equation here where we have rho times V, and we're going to input V as this here, Q over HW. So we'll have Q over H times W, and then times D, and all that over mu as well. And then now we can define our fanning friction factor, which will just be from our Churchill equation, and we will input the Reynolds number, and our surface roughness will be 1 e to the -6. And now what will we return? So we're going to want to return the acceleration due to gravity minus our big equation, that we found on the whiteboard right here. So we'll have our fanning friction factor times Q squared times 2HW H plus W and all that is over 2 sine theta two times numpy sine theta times H times W to the third. So now we do need brackets around this whole thing. And then now we can use our root solver, where we supply the equation, an initial guess, which we're going to call 0.2. And then we can extract the part of the array that we want, the answer. And we should get this should be lowercase. Should get 0.1406 as the height of the liquid in our rectangular channel.